Okay, Unit 2, Day 3. We're going to talk about synthetic and long division now. So this is going to be going along with section 2.3 in your book. But before we do that, let's talk about this problem. This is a good problem. So we've got a piece of paper, and we're going to fold that piece of paper into a box with an open top. And it's going to have these weird little locking tab thingies, if you can notice, are just like an extra little fold in the paper that will fold in and secure it closed. So, first thing we want to do is write an equation that represents the volume of this box. And to do that, we have to recognize we're talking about length times width times height. So let's see if we can come up with an expression for the length and the width and the height of this box. So if you think of that side of the box right there, that is going to correspond to this bottom side right there, or equivalently that top side right there, which is going to have an expression of 24 minus 4x, because we've got 1, 2, 3, 4 x's we're taking out of it, which I'm going to factor as 4 times 6 minus x. And then that side right there will correspond with that side there. And that is going to be 24 minus 2x, because there we just have the 1, 2x we're taking out this time. And again, I'm going to factor that as 2 times 12 minus x. And then finally, don't forget, we do have the height of this box, which is going to be x. So if we do the volume in terms of x is going to be length times width times height, which gives us 2 times 4 is 8 times our height x times our two factors 6 minus x and 12 minus x. So as a function, this function will continue on forever in negative x and positive x world, but in the context of this problem, since we're dealing with physical limitations of the non-negativity of real things, we have to be looking at this factor right here, because we're going to want our x's to be between 0 and positive 6. Because if they're any bigger, then that factor is going to give us negative values, and that would mess us up, because then we get negative volume, and that's not a real thing. So our domain has to be between 0 and 6, including both of them is technically fine for what we're dealing with. Might not make a real box, but that's good enough for us for now. So let's sketch the graph here using what we know. We know we're going to have zeros at x equals 0, and we're going to go 1, 2, 3, 4, 5, 6, and I'm going to have another 0, and then I'm going to have another 0 way out here at 12, but again, I'm not really too concerned about that, because that is off in fantasy land where we don't exist for this function. So think about the degree of this function. This is a third degree function, degree 3, x cubed. The leading coefficient is going to be positive, so our tails are going to be down and up. So I'm going to come down, go up like that, and come back down, and my graph would continue down like that and come back up like that. But again, I'm only interested in that part in the real world, positive x, positive y right there. Now, real quick, let's talk about our zeros. Since the multiplicity of each of those zeros is 1, that's why I know I'm crossing at all of these 0 points instead of bouncing. So let's estimate an x value that will maximize the volume, and then let's find that volume. So we're going to get a maximum value somewhere around here. Now this isn't a perfect sketch, so I don't know, but I know it's going to be roughly halfway between those 2 points is a good guess. So let's just for fun try the x value of 3. And if you plug that value of 3 into your function, into your v of x function, so we do v of 3, we're going to get 8 times 3 times 6 minus 3, which is 3, times 12 minus 3, which is 9. So 3 times 3 is 9, 9 times 9 is 81, so really we're talking about 8 times 81, which is going to be 648. So that point right there, maybe it's the maximum, maybe it's not quite, but it's 648 is our guess. So we're saying the volume is 648 when the x value that you cut off is 3 units. Now, when you actually when you actually graph this on your calculator, it's going to look more like something like that, like a little skewed to the left like that. And when you calculate that maximum value there, I do believe it's like 2.53 something, with a y value of like 670-ish or something close to there. I don't feel like redoing it. I made this whole video already and then it wouldn't process for some reason, so I'm stuck doing it again. So I'm going to be a little lazy. But plug those in, use the domain 0 to 6, and then once you do that, hit the zoom fit button and it'll automatically give you a nice window that shows you just that bit right there. Zoom fit will sometimes work nicely for you as long as you have a good domain to start with. So let's move on to what we're talking about today. We're going to talk about polynomial long division and synthetic division. So let's think about how we long divide normal numbers, because that's going to help us understand how we long divide polynomials. So if we want to take 9 and divide it into 536, we ask ourselves, does 9 go into 5? Well, no, 9 is greater than 5, so it does not. But 9 will go into 53. How many times? Well, let's see, 9 times 6 is 54. That's too big, so 9 times 5, which is 45, that'll go in. So I'm going to put my 5 up there above the 3 digit, and 9 times 5 is 45, and I'm going to subtract all of that. 53 minus 45 is 8, I do believe. Drop that 6 digit down. And now ask yourselves, does 9 go into 86? If so, how many times? Well, 9 times 9 is 81. And so, I'm sorry, I meant to write 9 there. 9 times 9 is 81, so we'll put that there. We'll subtract it, and we get a 5. And does 9 go into 5? Well, no, it does not. So I'm going to write this as 59R5. The 5 is our remainder. And we can say a couple things. We can say that 9 times 59 plus 5 equals 536. And we can also say that 536 divided by 9 equals 59 plus 5/9. Take a look at those for a moment and convince yourselves, yes, those are actually equivalent statements. All I'm doing is dividing by 9 on both sides from the top to get to the bottom. Cool. Keep that in mind for later. It's going to come in handy. So let's look at this one, long division with an actual polynomial. Well, we're going to set it up the same way. X plus 2 being divided into x squared minus 6x minus 16. Now, sort of ignore the 2 for now, just focus on that x. You're asking yourselves, how many times will x go into x squared? Well, I know that x times x is x squared, so it's going to go in x times. Ooh, I just spit on my screen. So x will go into x squared x times, and but then you have to take that x times and multiply it by that whole expression, not just the x, but the x plus 2, because it is all there. So I can say that x times x plus 2 is going to give me x squared plus 2x, and I'm going to write that underneath. And now I need to subtract that entire expression. So x squared minus x squared is 0. Negative 6x minus 2x is negative 8x. And just like before, I'm going to drop down my negative 16. I'm going to make that look like an 8 a little bit more. And now I'm asking myself, how many times does x go into negative 8x? Well, it's going to go in negative 8 times. And negative 8 times x plus 2 is going to give me negative 8x minus 16. Oh, so it went in negative 8 times, and that gave me negative 8x minus 16. Notice that the two expressions there in the bottom two lines are equivalent, so when I subtract the bottom one from the top one, I will get 0. That 0 is telling me that I have a remainder of 0, which tells me that x squared minus 6x minus 16 divided by x plus 2 equals x minus 8. So essentially, I just factored this polynomial, this quadratic. And you could have done that in your head, but this is, it's our first example. We're going to look at trickier ones like this one. Oh, this one's not actually trickier, but let's do it anyways. So we're dividing x plus 5 into 3x squared plus 3x minus 60. So ask yourself, how many times does x go into 3x squared? Well, I need a 3 to get that coefficient, and I need another x, because 3x times x is 3x squared. So I'm going to throw my 3x right there. And then again, 3x times x is 3x squared. 3x times 5 is 15x. And I'm subtracting the whole thing, so you can think of that as flipping the signs on both terms. 3x squared minus 3x squared is 0. 3x minus 15x is negative 12x, and drop down your minus 60. Ask yourself, how many times does x go into negative 12x? Well, it goes in negative 12 times. Negative 12 times x is negative 12x. Negative 12 times 5 is indeed negative 60. And this is the part where you go, oh, Mr. Reed, you're so nice. You're giving us such nice numbers that actually work. Yeah, I am. We'll look at what happens later when you have remainders. Cool things happen. We'll look at that, but not yet. We're sticking with good answers for now. So again, that tells me that I can rewrite that quadratic 3x squared plus 3x minus 60 as x plus 5 times 3x minus 12. And at this point, let's actually factor it completely. So let's pull out that 3 and write it as x plus 5 times x minus 4. Notice I factored that 3 out of those two terms. La-da-da, because now I can look at it and be like, oh, my zeros are at negative 5 and positive 4. That's cool. So let's do one more example. Ooh, this time we are taking a cubic and dividing it by a quadratic, which means my answer is going to be a linear function. Think about that. 3 minus 2 is 1. Whoa! So, x squared plus 7x plus 10 being divided into 2x cubed plus 11x squared minus x minus 30. So, how many times does x squared go into 2x cubed? Well, it's going to go in, the x part's going to go in x times, I'm going to write that over here, my bad, x times, and the 2 part, well, I need a 2, because 2x times x squared is indeed 2x cubed, and 2x times 7x is 14x squared, and 2x times 10 is 20x. Notice I had to multiply that by each term of my divisor, x squared plus 7x plus 10. And also notice I wrote my 2x above my x term. It's a good idea to keep them in line. Your life will be easier. So let's subtract everything now. So we're going to subtract that 2x, we're going to subtract that 14x squared, and we're going to subtract that 20x. So 2x cubed minus 2x cubed is 0 again. That's always going to happen. 11x squared minus 14x squared is negative 3x squared. Negative x minus 20x is negative 21x. And now I'm going to go ahead and actually drop down my negative 30 as well. And now I ask myself, Rob, Mr. Reed, how many times does x squared go into negative 3x squared? Well, it goes in negative 3 times. Negative 3 times x squared is negative 3x squared. Negative 3 times 7x is negative 21x. Negative 3 times 10 is indeed negative 30. So again, those two expressions are equivalent, so I'm going to get no remainder, and life is good. I know that that is equal to 2x minus 3. So notice now this problem, how it differs from that last problem. Notice the numerators are the same. The denominator of this one I'm doing now was my answer to the last one, which tells me that my answer to this one should be x squared plus 7x plus 10. Let's make sure it is. So 2x minus 3 is being divided into 2x cubed plus 11x squared minus x minus 30. So 2x goes into 2x cubed, x squared times x squared times 2x is 2x cubed. X squared times negative 3 is negative 3x squared. And we will subtract both, so that becomes a minus and a positive. 2x cubed minus 2x cubed is 0. Still, 11x squared plus 3x squared is a 14x squared. Drop down that negative x. How many times does 2x go into 14x squared? Well, it goes in 7x times. 7x times 2x is 14x squared. 7x times negative 3 is negative 21x. Might be seeing some similar numbers here. Well, 14x squared minus 14x squared is 0. Negative x minus negative 21x is negative x plus 21x, which is a positive 20x. And drop that negative 30 down. And finally, how many times does 2x go into 20x? Well, it goes in 10 times. And I'm going to get 20x minus 30 again. They're identical, so my remainder is going to be 0. And x squared plus 7x plus 10. Oh, hey now, look, we didn't make any mistakes. Awesome. Well, that was a lot. Division algorithm, these are saying the same exact things. Again, just notice that this dx, we decided to multiply it by it on both sides. So then like that cancel, and you got dx qx, which was that, plus our rx there, and that was equal to those canceled to your f of x. Same thing, exactly like we did on the first normal number division thingy. So, synthetic division makes your life easy, but when can you use it? You can only use synthetic division when you're dividing by a linear factor. And if you are dividing by a linear factor, like say x minus 5, you're going to take the solution to that linear factor, in this case 5, write it by itself like that, and now you're going to transcribe, aka copy, the coefficients on each degree in descending order of degree, by which I mean do your cubic first, then your squared, then your x, then your linear term. I'm sorry, your constant term. So, I'm going to pull that 3 down, I'm going to pull that negative 17 down, I'm going to pull that 15 down, and then I'm going to cross over and pull down that negative 25, because it absolutely has to be in the correct order, higher degree to lower degree. And if you are missing a degree, like if there's no x squared term, you have to put a 0 in for it. So, this is how it works. Drop that 3 down, multiply 5 by 3. 5 by 3 is 15. Add negative 17 plus 15 is negative 2. Multiply 5 by negative 2. Each time we're just multiplying by that solution. 5 times negative 2 is negative 10. Then you add the terms in the column. 15 plus negative 10 is positive 5. And 5 times 5 is 25. Negative 25 plus 25 is 0. Again, that 0 is representing our remainder. If you get a remainder of 0, it tells you that that is indeed a factor of this polynomial. Now, interpreting your answer is pretty straightforward. We're going to get 3x squared minus 2x plus 5. If you think about it from right to left, it just builds up by a power of x each time. So this tells me that I can factor this as x minus 5 times 3x squared minus 2x plus 5. And then maybe you could factor that last part as well. If you can, you should. But let's look at another synthetic division problem. This one's kind of tricky, but let's break it down. Remember that we can only use synthetic division when we are dividing by a linear factor. So, if we factor this in our heads first, play the number game, then we can do synthetic division twice, which still sometimes might be quicker than doing long division once. So, ask yourselves what two numbers multiply to negative 3 and add to give you to 2. Well, it's going to be a positive 3 and a negative 1. So that tells me I have two solutions at x equals negative 3 and at x equals 1. So if I pull my, let's do the negative 3 first. If I pull my coefficients down now, I'm going to get a 2 for my x to the 4th term. I'm going to get a 4 for my x cubed term, negative 5 for my x squared, positive 2 for my x, and a negative 3 constant term. Now pull that 2 down, sorry. Negative 3 times 2 is negative 6. 4 plus negative 6 is negative 2. Negative 3 times negative 2 is positive 6. Negative 5 plus 6 is 1. Negative 3 times 1 is negative 3. 2 plus minus 3 is minus 1. And negative 3 times negative 1 is positive 3. And hooray, we get a remainder of 0, which is good because that tells me that x plus 3 is indeed a factor of that polynomial. But we have one more potential factor that we want to check, so let's check the solution of x equals 1 now. And notice how I'm just going to continue this down. I'm going to drop that 2 down again. 1 times 2 is 2, negative 2 plus 2 is 0. 1 times 0 is 0. 1 plus 0 is 1. 1 times 1 is 1. Negative 1 plus 1 is 0. So again, interpret this answer. We get 2x squared plus 0x plus 1. So this can be factored as x plus 3 times x minus 1 times 2x squared plus 1. And that's as far as I can factor that today. After tomorrow, we will be able to factor that completely using complex numbers. Cool. So, let's look at this last one. We've got x equals 2 and x equals negative 3 are solutions of f of x, and we want to sketch this function without a calculator, so we need to figure out what the other solutions are. So again, just use some synthetic division. When given the option, I always use synthetic division over long division. So let's go with our first solution, 2, and then pull down your coefficients, 2, 7, negative 4, negative 27, and negative 18. Drop it down. Pull that 2 down. 2 times 2 is 4. 7 plus 4 is 11. 2 times 11 is 22. Negative 4 plus 22 is 18. 2 times 18 is 36. Negative 27 plus 36 is positive 9. 2 times 9 is 18. Negative 18 plus 18 is 0. Hooray, that was quick. It can be just that quick for you too. So now let's check our other x. Negative 3. Boom, boom. Drop it down again. 3 of a negative sort times 2 is negative 6. 11 plus negative 6 is 5. Negative 3 times 5 is negative 15. 18 plus negative 15 is 3. Negative 3 times 3 is negative 9. Alas, we get our 0, telling us that negative 3 is in fact a solution as well. So now I can write out my factors as x minus 2, because of that x equals 2 solution, x minus 3 plus 3, because of that minus 3 solution, and 2x squared plus 5x plus 3 from the solution of that synthetic division party. So now let's factor this completely, because I still need to find the solutions of that last bit to find my zeros. So I'm going to pull that 2 out. Maybe you do it differently, that's okay, but I'm going to pull the 2 out front, and then now let's factor what's left behind. Well, what's left behind is x squared plus 5 halves x plus 3 halves. You probably don't like to play with fractions like I do, but that's okay. Get used to it. They're cool. You don't have to do it this way, but that's how I like to do it. So at this stage, I'm going to factor this as x plus 3 halves and x plus 1, which I'm for the time being going to write as 2 halves, because we can check ourselves. 3 halves times 2 halves is 3 halves, because you get 6 over 4, which is the same as 3 over 2. So we're good on that end. 3 halves plus 2 halves is indeed 5 halves. So now that we see that, I'm going to go ahead and write it as 1, because this tells me I have zeros at x equals negative 3, negative 1.5, negative 1, and positive 2. And my leading coefficient is positive. My degree is 4, which is even, so it tells me that my tails are up and up. And now I can sketch in the graph of this function. So I'm going to go 1, 2, 3, and 1, 2. Let's give myself some zeros at negative 1, negative 1.5, negative 3, and positive 2. And I'm starting up and I'm ending up and I'm crossing through all of my zeros, because the multiplicity of each zero is 1. So I'm going to look something like that. Now that looks kind of poopy. I'm not very good at doing this here. But also let's think about something else. We know that my y-intercept is negative 18. So I know that that point right there is negative 18. And we could plug some other points in, like we could plug in a point right there, like say negative 1.25 to get an idea where we are there. We could check this point, maybe negative 2.25, to see what that is, and it will give us a better idea and make our graph look better. But we're totally super incredibly done.